welcome to lecture number 20 in this video course series on silicon and wide bandgap power devices. I'm Professor Anant Agrawal with the Department of Electrical and Computer Engineering at the Ohio State University. I'd like to acknowledge the help from Dr. Arash Salami, whom you heard in the last two lectures describing the fabrication and processing and layout of silicon carbide Schottky diodes. Also acknowledge the support of Office of Naval Research. So with that, let us get started. So in the last lecture, we had covered a simple MOS transistor. This is also called a lateral MOS transistor because we have source and we have drain all on the same side. We have a gate oxide SiO2 and we show it as a metal gate that's only historical. These days it's made out of polysilicon doped with phosphorus to make it a N plus polysilicon, highly doped N type polysilicon. We have a P body of the transistor, and as we had explained to you, when we increase the gate voltage, we create a depletion region here in the P type semiconductor, and then if we increase the gate voltage above a threshold value, then we induce a layer of electrons here, which we call inversion channel, and that inversion channel has a high density of electrons which conduct current as voltage is applied from drain to source. So as drain voltage is positive, the current electrons flow from source to drain, and the conventional current flows from drain to source. So we went through all this. When the gate voltage is 0 or below the threshold voltage, we only have depletion in the P-type semiconductor. There is no conduction possible between source and drain because there is no inversion layer, and that's called the off state. So the transistor is on when gate voltage is higher than the threshold voltage. Transistor is essentially off when the gate voltage is below the threshold voltage. And we had mentioned that threshold voltage depends on many things, among them the doping, the type of semiconductor, the metal work function difference, and positive charges in the oxide and interface states here at that interface. So all that is very complicated and we will not cover that in this course, but it suffices to say that threshold voltage is of the order of 2 to 3 volts for these devices. All right, so now let us say we want to make a vertical power transistor, and here is a structure which is called the MOSFET structure for high voltage. And MOSFET is a terminology from silicon times, and we have simply adopted the same technology in silicon carbide and also the same terminology, and we also call it MOSFET. So anyway, the first silicon carbide MOSFET was introduced by Professor Jim Cooper of Purdue University, so we acknowledge him here. And just looking at this structure, we can see that the lateral MOSFET structure we showed you in the previous slide is actually present here and here. So here is your P semiconductor, here is your N plus source, and your drain is at the back, but the drain, this whole region is N-type, so this corner could act as a N plus drain. Same thing on this side, we have N plus source, P semiconductor, and the drain here. The real drain is at the back, but all I'm saying is that there is a lateral MOSFET present where the current could flow from drain to source in the lateral direction. So then here is the gate, which is made out of polysilicon. Here is the gate oxide, and here is the source contact. And along the source contact, we have shown that there is a P plus region which contacts this P base. So the source metal shorts the N plus to the P base. So this is called the body contact, and in this case we have shorted the body contact with the source. So now and this whole thing is called the drift layer. Here is the substrate, which is typically 10 to 12 mils thick, something like 300 to 400 micron thick. Here is the N minus drift layer. This is a concept very similar to what we had talked about in PN junction and power Schottky diodes. We have a N-type drift layer whose thickness and doping depends on how much voltage we are going to drop across this switch. This region between the two P wells is called the JFET region, and so therefore we call it a JFET region. Now, the principle is very similar. Once we apply the gate voltage, which is higher than the threshold voltage, we are going to have an inversion layer present here and here. And because of this inversion layer, the current can flow from drain to source on either side. Both sources are connected together. So the current can flow from drain to source terminals through this inversion layer, which is induced at the surface by applying gate voltage higher than the threshold voltage. So we have shown several resistances here. So let's go step by step. This resistance denotes the resistance of the N plus source region because the current has to flow in this direction. This resistance is called the R channel because it represents the resistance of the inversion channel. This is called RJ FET, then this is called R drift, and then the R substrate. Sum of all these resistances will be the on resistance of this MOSFET when we turn on the transistor with a positive gate voltage. So the question is, what happens in the off state? So as we said, when we apply a gate voltage which is lower than the threshold voltage, let us say 0 volts, then there is no inversion channel here. These regions are not connected to each other. This resistance is basically infinite. So the electrons cannot flow across this region. And then we apply positive bias on the drain. You can see that basically the voltage will be dropped across this PN junction on both sides, right? So the voltage is dropped across the PN junction, and the region between the P wells, the JFET region, is fully depleted because as we apply positive drain voltage, this region will deplete from both sides. So, the JFET region is fully depleted and the depletion region extends into the drift layer, and that is where the voltage is dropped. So, let us just consider the off state first, which means we have a gate voltage of 0, no inversion layer, the voltage is dropping across this p-n junction. We can now consider on the next slide what happens. So, here is my p well, here is my drift layer thickness, here is the substrate, and we are applying positive voltage on the drain and the p plus is grounded. And you can see that we will deplete this junction mostly on the drift layer side, because this is lower doped than p plus. So, here we show that as we deplete along this way, the depletion region extends. The maximum electric field is at the interface between p plus and n, that means at the junction of p plus and n regions, and this maximum electric field rises as we increase the voltage and the depletion region extends to the right. Now, this is called a non-punch through structure. This is called the non-punch through structure because this n-type drift layer doesn't fully deplete before we reach the critical field at the interface. So, if we call this maximum field critical field E of C, when a voltage V is applied, we deplete this drift layer up to this point. We call this thickness WNPT, N for non-punch through, and the area under this curve, this line, so area of this triangle here will be equal to the breakdown voltage of the device. We neglect the depletion on the P side because it is so small. So, we neglect the area under this of this triangle here. So, the breakdown voltage is basically the area of this triangle, which we discussed before. It will be EM times WNPT divided by 2, and we replace the EM with the critical field EC of the silicon carbide. So, this is the non-punch through structure, and we had given you design equations when we were discussing the Schottky diodes and the p-n junctions. You can see that the width of the drift layer can be calculated from the given breakdown voltage divided by the critical field. The doping of the drift layer can be calculated from this expression, and the on resistance is given by this expression in terms of the breakdown voltage, the mobility, and the critical field. And these equations we had derived for you basically by using Gauss's law, and you can go back and review that. But it is good to understand that there is one unique solution for a given breakdown voltage. Once we know the breakdown voltage, we can calculate the doping and the thickness and the on resistance of this drift layer. So, now we know how to design the drift layer of a MOSFET for a given breakdown voltage. Basically, this is my drift layer. So, we will design the doping of this drift layer based on those calculations, and this is the P region, and we are neglecting the depletion on the P side. Then the other way to design this structure is called the punch through structure. And in punch through structure, as we increase the voltage across that p-n junction, we start depleting, and once we reach a voltage where we are fully depleted in the drift region, then the electric field, which is denoted here as electric field that punched through, is given by the Gauss's law, which is Q times the doping times the thickness divided by epsilon s. And this electric field is not equal to the critical field, it is below the critical field. So, this diode is not going to break down. That means we can apply more voltage to this diode, and as we apply more and more voltage to this diode, you can see that the depletion in the N plus region will start expanding, but this depletion would be very small because this is a very highly doped semiconductor. So, at some point as we increase the voltage, this field at the junction will reach the critical breakdown field of the semiconductor, and then at this point the semiconductor will break down into avalanche. So, now the voltage can be calculated by taking the area under this trapezoid and essentially neglecting the area of this triangle here because this is so small. So, the area under this trapezoid is basically calculated from this figure. You can see this triangle here is the same as this triangle here. So, we can calculate the total breakdown voltage by taking the area of this rectangle, which is critical field times the thickness W dpt, and subtracting this triangle, which is the same as this triangle, and the area of this triangle is simply given by that field times this thickness divided by 2. So, this is something we had discussed before. This is called the punch through structure, where we fully deplete the n-type drift layer, and it turns out that there are many possible solutions for this. There are many different combinations of doping and the thickness for a given breakdown voltage. So, there is no unique solution or there is no unique design for punch through case, because we have infinite number of combinations of the doping and drift layer thickness for a given breakdown. So, last time we had also discussed this, and we had basically calculated the breakdown voltage for the JBS diode case simply as the area under the trapezoid, which we just showed you, and then the resistance of the drift layer would depend on the thickness of the drift layer and the doping and mobility of the drift layer. So, we have written an expression for the on resistance of that drift layer, and what we want to do is maximize the breakdown voltage and minimize the on resistance. So, if we take the ratio of R on over the breakdown voltage and we minimize that to find the optimum combination of the doping and the drift layer thickness, we end up with these expressions. I will encourage you to derive these expressions. This is one optimum solution which gives you the doping and the drift layer thickness for the punch through case and the on resistance for that drift layer for the optimum case. And if you compare this resistance with the resistance of the non-punch through case, you will find that this is approximately 86% of the resistance in the non-punch through case. So this is leads to the punch through design leads to 14% smaller on resistance. So in that sense, it's a better design. Most of the silicon carbide MOSFETs are designed using this approach. So here we have taken a silicon example and we have done a design of breakdown voltage versus the doping concentration, and we have changed the drift layer thickness from 5 to 10 to 20 to 50 to 100 micron. So for these different thicknesses, we have changed the doping and we have calculated the breakdown voltage. This red line here basically shows the unique solution for the non-punch through case. The other name for that is parallel plate junction, and that's always a unique solution. So for a given breakdown voltage along this red line, we have a unique solution of the doping and the thickness you can get. Now, under the red line, these curves represent a punch through design. So for example, this curve, anywhere along this curve, which is 5 micron, the doping and the corresponding breakdown voltage is shown here. So as we change the doping, the breakdown voltage will change as long as we keep the drift layer thickness the same. Then we have done the same thing for 4H silicon carbide, but we have used a higher critical breakdown field for silicon carbide. Now, let's take the case of, let's say we are designing a 1000 volt diode in a non-punch through mode. So the 1000 volt point is right here on this red line. So we'll roughly design that diode with perhaps 6 micron of epi and 2 times 10 to the 16 doping, right? So since the resistance of this drift layer is proportional to the drift layer thickness and inversely proportional to the doping, you can calculate the on resistance for the non-punch through case for 1000 volts. So remember these numbers: 6 micron thickness, 2 times 10 to the 16 doping. Now, if we go to the silicon case to do the 1000 volt design, you can see that we are roughly looking at, if I can just move this laser pointer to the right spot, but you can imagine this 1000 volt case will roughly use 52 micron of epi and maybe less than 2E14 doping. So you can see that compared to silicon carbide case, we have a much thicker epi, 6 micron versus 52 micron, and much lower doping. It was 2 times 10 to the 16 there, and it's less than 2 times 10 to the 14 for silicon case. So that means the on resistance of this device in silicon for 1000 volt would be about 1000 times higher than the silicon carbide case. So this is the advantage of using a silicon carbide material because it has high breakdown field. We can design a device which much thinner drift layer and much higher doping. All right, so let's talk about other regions. So far we have focused on designing this drift layer under the P base, and now we can design it with a non-punch through case or a punch through case and determine the doping and drift layer thickness for a given breakdown voltage. And we have shown a half cell of this MOSFET here, and we have shown you before that the current will flow along the inversion channel here when we apply positive gate voltage higher than the threshold voltage. Now, we had also said this is the JFET region, and we are only showing you half the cell. So, this is half JFET region. The other half would be on this side. Then in the off state, when the gate voltage is below the threshold, this device is off, and this PN junction, as we discussed, is blocking the voltage across this drift layer. It is worthwhile to examine what is happening along this line AA prime, which is drawn in red here. And we also know that when we apply high drain voltage, we will also deplete the JFET region. So, the depletion will extend vertically and laterally from this P well. So, it is worthwhile to examine that electric field at point A along this cut line, which is the center of this JFET region, and that electric field, let us say, is electric field in silicon carbide, and immediately to the other side of this interface, the electric field would be in the oxide. And if you take the ratio of that electric field in the oxide versus the electric field on the silicon carbide side, it should be the ratio of the dielectric constant, which is approximately 2.5 for silicon carbide. So, you can see that electric field in the oxide is amplified, electric field in the silicon carbide is amplified by this factor 2.5 in the oxide. So, the oxide field is 2.5 times higher than field in the silicon carbide. But we know that oxide is not going to be very reliable at very high fields, although the breakdown field of oxides is like 10 megavolt per centimeter. But it has been shown that for reliable operation, that oxide field should be limited to 4 megavolts per centimeter. So, if we look at this ratio and we limit the oxide field to 4 megavolt per centimeter, then we should limit the silicon carbide field to 1.6 megavolt per centimeter at point A when we have applied the full breakdown voltage on the drain. So, now we begin to see that if we are going to limit the breakdown field of silicon carbide to 1.6 megavolt per centimeter, then perhaps we are not taking full advantage of the breakdown field of silicon carbide, which is in excess of 2 megavolt per centimeter. So, fortunately, some clever design comes to our help. So, here we have shown the same half cell except we have added this P plus shielding region. This is higher doping at the bottom of the P well, which is not important for this discussion. Here is our P well, and here is the point A again, and here is the cut line. So, now if we basically vary this junction, and let us say this junction depth or WJ-FET, the half width of the J-FET, there is a small typo here. This should be half WJ-FET because we are only showing you half the cell. You can see, and if we plot the electric field as a function of this distance for different voltages, and let us just focus on the 3000 volt curve, you can see that if this field, and we are plotting the electric field along the A prime cut line versus the distance along A prime A, you can see that if we apply 3000 volt, the electric field in the substrate is 0. As we move towards the gate, electric field increases, reaches a maximum, and then it drops to a very, very low value, in this case about 1.5 megavolt per centimeter. So, what that is telling us is that electric field at this interface on the silicon carbide side can be made to be small, like 1.5 megavolt per centimeter, so that the field in the oxide will be below 4 megavolt per centimeter. And the trick in doing that is to choose a small J-FET width so that this happens. So, you can imagine if this is very large, then this is not going to happen, and this electric field would be very, very high at point A. But if we reduce the J-FET distance or J-FET gap, then this electric field is reduced at the surface because this J-FET region is fully depleted from both sides by the two P wells. So, this is a two-dimensional simulation, and we cannot do the one-dimensional analysis. So, we will basically show you a lot of simulations to show you that this indeed happens, and it is a function of doping and the width of the J-FET region. I think this is a good stopping point for this discussion, and today what we have discussed is the vertical MOSFET structure, two modes of breakdown design. One is the non-punch through, the other is punch through. We showed you the equations for non-punch through and punch through. We said the punch through design is favorable because it leads to lower on resistance. And then we discussed the off state and showed you that we need to reduce the electric field at point A in silicon carbide, so that the field in the oxide will not exceed 4 megavolt per centimeter, which for reliability reasons, for long-term reliability reasons for oxide. So, next time we will consider the on state when we turn on the gate above the threshold voltage, then current starts flowing, and then we will calculate different resistive components of this MOSFET in the off state. So, Until then, thank you, and please look at this material in your own time, and we'll meet next time. Thank you.